checks after this before class. Stranger things have happened. There's no hope for grading the test before class. That's not even. But quiz I can grade more carelessly.
Do you grade yourself, or is Julia?
I could have Julia do it, but I think I'll grade the quiz just because, it's a quiz. But anyway, I'll begin with a word of prayer. Heavenly Father, we thank you for this class, for this time we have to study your creation. Just pray that you would just guide my steps today, help us to understand a little bit more about proofs of perhaps the inverse or the implicit function theorem, at least in principle, how these proofs are made, and just to give us more insight into the contraction mapping principle and its importance to mathematics. Lord, in your name I pray, Lord Jesus. Amen. So, all right, so essentially I'm endeavoring to hit the high points of about 30 pages of this book, C.H. Edwards, Jr., Advanced Calculus of Several Variables, and I had said something about the continuous differentiability issue being something that's like functional analysis. That's not accurate, I don't think. I think it's actually all finite dimensional stuff, but it's a little bit abstract. But anyway, that book actually has an explicit proof that continuous differentiability of the partials means a continuous assignment of the differential. But it does it in the context of analysis on like finite dimensional space, actually, I believe. Now there is a chapter at the end of that book which is on variational calculus. There it does get infinite dimensional. And at the end of the book there is actually at least a proof sketch of like the I think the implicit function theorem for a normed linear space of possibly infinite dimension. So there is some aspect of infinite dimensional analysis in this book. And so what that means is that the argument for the implicit function theorem that we could give today, it can be still given in a much more sophisticated context, I suppose. Now this stuff I did last time. I noticed that if you go on in my notes, I actually have all the calculations we did and more. Like it's just like it's at page 108 is where I actually circle back and did some. I think I was rediscovering some of the things I did in the notes a little bit later because I was focused on like page 99 or 100, and if you skip ahead to like page 108, I think that's some of what I was doing. Just wanted to say that. All right, so let me erase this and let's talk about the contraction mapping principle. Although I think maybe first I should talk about, do things in order here. I got some sticky notes to try to keep me on point. I follow my sticky notes. All right, my sticky note says contraction mapping first, so let's do it. I didn't talk to you about this yet, did I?
No.
Okay.
This is looking in the library. What's the name?
This is Advanced Calculus of Several Variables by C.H. Edwards, Jr. I don't know if it's in the library or not. I probably didn't ask for the library to have it, and it's a Dover book. You can get a copy of this thing for not too much. I do have a copy at home I can lend you. I just need to bring it. If you want me to, I can.
Edwards, C.H. Edwards.
Yep, C.H. Edwards. It's in the library?
Yeah.
Okay. I must have put it there at some point.
But it's online.
Oh, okay. Well, that's better, right? Okay, so I'm, of course, in the Dover edition. I don't know which edition you got there. But so we'll start out talking about the theory on just the reals. Pretty much everything we do here generalizes, but I think for the sake of being concrete and giving a careful starting point, let's just follow the book and I'll do it here. So I've got a mapping from the closed interval a to b to the closed interval a to b, all right? It's called a contraction mapping. All right, contraction mapping with contraction constant k less than 1 if the absolute value of phi of x minus phi of y is less than or equal to k times the absolute value of x minus y for all x, y in AB. So the contraction mapping theorem asserts that each contraction mapping has a unique fixed point. So what's a fixed point of the contraction mapping? A fixed point would be x star such that phi of x star is equal to x star. Again, that would be a fixed point of the contraction mapping. All right? So usually the game that's played in using the contraction mapping is to design a contraction map somehow or another such that the fixed point produces whatever kind of thing you're trying to, to show its existence. So you try to arrange things so that the fixed point's existence gives you the solution to whatever kind of equation you're trying to solve. Now it's a little bit of an art form how to do that, but we'll hopefully see a couple examples today. Now the theorem, which we should prove, is this. So we'll have phi of contraction mapping as above, then phi has unique fixed point x star, right? Phi of x star equals to x star. All right. Moreover, the sequence xn n equals 0 to infinity, excuse me, defined recursively by x of n plus 1 is equal to phi of xn. All right, well, that's pretty simple. Converges to the fixed point. Oh, that's nice. Moreover, well, in particular, I already used a moreover, so now I'm back to in particular. Trying to keep my English varied here. It's not my English either. I'm just reading out of Edwards here. But check this out. xn minus x star is less than or equal to k to the power n times the absolute value of x naught minus x1 divided by 1 minus k for each n. So this is just beautiful, a really beautiful theorem, because you see what's going on here is not only is it telling you, that if you can construct a sequence by just iterating the contraction map, right? Not only if you can do that, well, then the sequence converges. But not just that, you get a really pretty concrete estimate on the error in your nth iterate. Just like that. Like that's really quite simple. And that's why this is actually a very important theorem to numerical methods people, right? Like, did you take numerical methods with Dr. Wang?
That's the only upload.
Okay. I wouldn't be surprised to find Dr. Wang talking about this in numerical methods. I'm not sure he does, but okay, so let's prove this. So here's the proof. We look at the absolute value of x of n plus 1 minus xn. All right. And what's that going to be equal to? In terms of the iteration, what's that equal to?
That's phi of xn. I mean, the modulus of phi of xn minus phi of x.
Ah, right, very good. Precisely. So that's phi of xn minus phi of xn minus 1, right? Which is what? Less than or equal to, by assumption of the contraction, less than or equal to k times the normal, the absolute value rather, of what?
xn minus.
Right. And so he says, so it follows easily by induction that, all right, so then what do you do? Like, let's just play this game a bit. And we can do that again, right? So this would be less than or equal to k squared times xn minus 1 minus xn minus 2. Because you see, we had n plus 1 and n switched to, these just go down by 1. Junk, 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 junk. So this keeps going, right? Until eventually you get to k to the power n times the absolute value of x1 minus x0. And I neglected something here, my bad. I have more of the sequence defined by that, and here's what I forgot to write down. It's kind of important. x0 is an element of a to b, all right? It's just got to be some point, all right? Okay. And and we can't go further than this, right? Because we're out of points in the sequence to do stuff to. All right, fine. And anyway, you don't need to. All right, so check this out. And to make this precise, of course, you could do a formal induction. All right, it's kind of obvious. All right, so then consider, if we look at the xn minus xm, and we're going to assume 0 less than n greater than m. All right, so we're looking at kind of a Koshi condition here, right? We're looking at the difference between points that are sufficiently far out in the sequence, right? Well, okay, so then this, by the triangle inequality, well, let me just first of all say that this is equal to what? This is equal to the xn minus 1 plus xn minus 1, right? And then what I can do, what? Minus xn minus 2 plus xn minus 2, right? Plus dot 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 plus, well, minus xm minus 1 plus xm minus 1 minus xm, right? Maybe it's supposed to be n plus 1, rather. Plus 1, yeah. Remember, m is greater than n, so this makes sense, you know. Anyway, so we basically just add 0 creatively, and then, of course, triangle inequality, that is this, right? xn minus x, that was supposed to be n plus 1, my bad. I should have done n plus 1, okay? Not n minus 1, dummy. Me, not you. And that should have been n plus 2 plus 2. Eventually we get to, so I had it exactly backwards, m minus 1. I'm so sorry. There we go. Okay, fine. My bad. Because n is less than m, so I've got to kind of work my way up to m. Anyway, so xn minus xn plus 1 plus the absolute value of xn plus 1 minus xn plus 2, right, plus da 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 da. Eventually we get to the absolute value of xm minus 1 minus xm, right? And then we use the claim that's right above to replace those with what? Well, that's less than or equal to what? So the first one gives us a k to the power n. The second one gives us a k to the what? So we go from here to there. So we take 1 away from This should have been n minus 1, shouldn't it? If I'm going to use this right here, I've got this n plus 1 here, right?
Yeah.
Puts an n here. So if I've got,
N minus 1.
oh, I'm a dummy. I gotta flip the script on these, right? So this is this. You see, I gotta turn these around, right? They're the wrong order. I should take the larger one is what governs the k. So, duh. So the 1 less than n plus 1 is kn. This one gives me n plus 1. Finally, I get to k. M, I think, minus m minus 1, yeah. Yes. Times that x1 minus x naught, which is just some fixed thing, right? All right. You follow?
I think so.
So then what can you do? How about just keep going, right? I mean, this is going to be less than, if k is positive, I mean, I guess k could be 0, right? But fine, so I'll put less than or equal to, because k could be 0, fair enough. But we've got, we could replace that with like 1 plus k squared plus dot 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 dot, right? x1 minus x0. So I added, it went that way, just, and I can do that. That's a geometric series. You see? Because the k is less than 1, it converges. In fact, this is straight up equal to x1 minus x0 over 1 minus k, right? All right. Now, does this prove that the sequence, the iteratively defined sequence, is a Koshi sequence? I think the last thing I wrote maybe doesn't. Because that's like, whatever that is, it's fixed, right? It doesn't depend on n at all. But if you look at as n and m, let's say as n goes to infinity, right? This can be made as small as possible, right? Because k is a number less than 1, so you can control this to be as small as you like, and like I can specifically replace this with the the formula for the nth partial sum. I can use the nth partial sum of the geometric series to come up with a concrete thing to put here, and I can prove that this is in fact a Koshi sequence. I think it's enough to see that. So this implies thus this is Koshi, which implies that xn goes to x star, right? And that x star has to be an element of a comma b, you see, because it's a Koshi sequence in the closed interval from a to b, so it must converge to some point within ab, because ab is a closed set. So if you have a convergent sequence in a closed set, it has to converge to a point within the set, right? Because a closed set contains all its limit points. So that's an element of AB. And then more than that, then you can see from just looking at this, right? If you just take the limit, right, as m goes to infinity, let's say, of this, well, then that's equal to xn minus x star by the continuity of the absolute value function and the fact that that goes to x star. And of course, that is less than or equal to, by just the usual, comparison theorems for limits of sequences, I have that this is greater than that. Taking the limit as m goes to infinity, of course, this is easy to take the limit as m goes to infinity. It's just straight up x1 minus x naught over 1 minus k, right? Oh man, wait a minute. I think I've not done this right. Because it was more delicate, wasn't it? My bad. I see. Here's where I actually need to get into I mean, that's true, but it's not interesting, right? That's true, but it's not true, but not interesting. That's the maximum error in the sequence, as it's compared to the limit, the ultimate. What I should have done would have been more nuanced, right? Is to remember that, how's it go? If we have 1 plus k plus da 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 plus k to the power n, I think we get 1 minus k to the n plus 1 over 1 minus k. So if instead of going all the way to infinity, like don't do that. If I just, go all the way to all the way back to 1 and go to the km minus 1, right? Like that, then this is straight up equal to, if I believe my math here, 1 minus k to the m over 1 minus k, I think. Norm of x minus x naught. I may have messed that up though. I think I can do better though, like, still not doing it quite right. I'm sorry, Ernesto. Oh, dummy. I'm a dummy. What should I have done here? I'm sorry, I'm butchering this. Golly, I can't, it's so embarrassing. This is beautiful, and I'm ruining it.
But how is this proving
I'm just ruining it.
the inequality of where we have x1 and x star?
Yeah, that's what we haven't proved yet. That's what I'm fussing about. So what I should have done is I should factor out k to the n. That's what the book has. I factor out the k to the n. Then that leaves me with like a 1, plus k plus dot, right? Times the absolute value of x, x1 minus x naught. All right. And then that is equal to k to the power n over 1, k to the power n over 1 minus k, absolute value of x1 minus x naught. Okay, there we go. So then, as I was saying down here, again, same argument. Take the limit as m goes to infinity of this, right? Well, this is less than so by passing the limit inside the absolute value, I get that. All right, but on the other hand, I have that it's less than or equal to the limit as m goes to infinity of all this, but there is no m dependence here, so that simply gives you k to the n times absolute value of x1 minus x naught over 1 minus k, which was precisely the estimate we're trying to show. Okay. Now what's left to prove? Allegedly, it's a unique fixed point, right? So how do you prove uniqueness usually?
Suppose there's two.
Suppose there's two, right? So let's do that. If we had a second one, if we also had phi of x star star equals to x star star, right? Then we should be able to prove that they have to be equal. Let's see how the argument goes. Well, first of all, Edwards says that condition 3 implies that phi is continuous on AB. What condition? Well, condition 3 is this right here. This is condition 3. Do you see why that says that phi is continuous on AB? Let epsilon be greater than 0. Choose delta equal to epsilon over k. Then you get the difference of that is, okay, yeah. So yeah, it's clearly phi is continuous, and as such, we can calculate. Well, I'm not quite to uniqueness yet. I guess I'm this. Oh yeah, this is the other thing I haven't done yet, right? So the limit. Phi of x star, right, is the limit as n goes to infinity of phi of xn, right? Which is the limit as n goes to infinity of xn plus 1.
How does that prove that?
Which is x star. Oh, this does not prove uniqueness. What this proves...
I'm thinking in the convergence part. Can that be any arbitrary?
What are we... which one? What part are you fussing about? I'm not...
We proved the convergence to x star.
Oh, so yes. Why? This is a Koshi sequence of real numbers. Which implies that there exists a limit, which we call x star. So this is by the completeness of the real numbers.
Okay, I see.
So Koshi implies convergence, that it's a Koshi argument.
That makes sense.
Right. Now, one of the things we should be thinking about as we're thinking about these things is, you know, how is this going to generalize to like Rn, you know? Like, there's some things you can kind of anticipate, right? Like, we're gonna need some kind of analog for the closed interval for n-dimensional space. All right, that's one thing. It's fairly obvious what's going to happen. We're going to replace absolute values with the norm, right? With the length of n vectors. And with that in mind, then these are all going to be norms. And this is still going to go through. But now it's going to prove that you've got a Koshi sequence of vectors. But in our Rn is complete. So the whole, as long as we can come up with a suitable analog of the closed interval in Rn, we got a shot at generalizing the contraction mapping theorem for a sequence of n vectors subject to the contraction. Okay, so uniqueness. How do we get uniqueness? We have the fixed point because this is the continuity of phis that you can pass the limit outside, right? The limit, that is by definition the limit as n goes to infinity of x of n. Pull that out, but then by definition of the sequence, that is xn plus 1. But of course, as n goes to infinity, this also goes to x star, right? By the usual substitution rule for infinite limits. Now, so how about uniqueness? We should prove uniqueness. Let's prove uniqueness. Well, what he does is to look at, and I'll do it in purple here. He looks at the difference between your fixed points, x star minus x star star. All right. And he's like, well, they're fixed points, right? So that, of course, would be phi of x star minus phi of x star star, because they're fixed points, aren't they? But that would be less than or equal to k times the absolute value of x star minus x star star. Why does that prove they're unique? See, k is what? Less than 1. So that means that this is less than. Well, anyway, I don't need to do, I guess it's true, but I don't know if that really helps. The point is, if you look at this, since k is less than 1, it follows that this must be 0. Yeah. All right. And that's the contraction mapping theorem. Now let me apply it to something concrete, okay? Still not getting to multivariate analysis at the moment, but I think it's important to see this because you didn't do it in real analysis, right?
Doing this?
No. I would definitely do this if I was teaching reals. It is not in the culture of the way real analysis is commonly taught. Because real analysis has sort of a tendency to shy away from calculational methods these days, which is unfortunate because the need for rigor is most powerfully shown when you show that being rigorous gives you a better estimate for something, right? So like that, to me, that's why this is just a beautiful piece of mathematics, because it's analysis, but it also has given us a specific calculational something there, you know, and it's also deeply real analysis, right? Like notice how the use of the Koshi criteria comes into play here, the convergence of the geometric series, like it's got so much in it. It's a wonderful thing for real analysis. But I'm content to not teach that course. Don't misunderstand my words. So, okay, so I gotta find, I didn't put myself a sticky note. And now I'm not taking my own advice and I'm covering something I didn't have a sticky note for. This is probably a bad move, but I'm gonna do it. So here's the theorem. This is Edwards' theorem 1.2 on page 164, okay? And so I won't prove all of this. I'll just try to do enough so you can understand it. So here we have f is a mapping from AB to the reals. Differentiable function. It's a differentiable function, and we're going to assume that f of a is less than 0 is less than f of b. So that tells you right there that there's hope, all right? There's hope, what? What does that criteria right there tell you about this function? So what you're looking at, you might call a modified Newton's method. It's modified Newton's method because the iterate is not based, well, you know, maybe this is just, I don't know, there's a lot of variations on Newton's method, but here's one anyway. There is like a more numerically simplistic one. If you can put a bound, like a maximum on the slope, you can kind of soup this up so that your iteration goes faster. You notice I'm still needing to evaluate the function here. I guess I have to do that. I guess you have to evaluate the function, otherwise you don't know that you actually got. Well, anyway. So this is Newton's method. So the proof of this is the contraction mapping theorem, right? So have you ever seen Newton's method?
Yeah.
You know what? Okay, so you know what? We basically just look at the tangent line and try to solve for it for where it's 0. So this is like basically taking not the tangent line, but it's kind of like taking the line of maximum possible slope and looking where that goes to 0, and just always following the line of maximum slope to the x-axis rather than following the tangent line. So it's a modified Newton's method. It's not quite Newton's method. But what should we try to show is what's our alleged contraction mapping here? Phi of x equals to what? Apparently, phi of x is equal to x minus f of x over m, right? If you look at this formula, you can see that apparently that must be my contraction map. Okay, so why is that a contraction map, I guess? It's a question we can ask, right? So let's look at what happens when we take like phi of x minus I guess I can use x and y. It'll probably be okay. Phi of x minus y, right? Well, that would be equal to my bad. Yeah. I'm supposed to look at phi of x minus phi of y, right? So let's look at that. Phi of x minus phi of y. All right? That is equal to what? If this is my definition, I've got x minus y minus what? 1 over m, right? F of x minus f of y. Okay. Now, can you tell me anything about this? Now, this, of course, is for what? Here I'm dealing with, without loss of generality, a less than, I guess it could be equal to, I don't remember. I guess it could be equal to x. I can like less than y, less than or equal to b, okay? What can I do with this? I've got a difference of function values. I've got a differentiable function, which is, of course, it's continuous and differentiable on the interval of consideration. I can use the mean value theorem, right? So the mean value theorem says that this is straight up equal to x minus y minus 1 over m times what? Well, times, you know, f prime of c, let's say, times, well, x minus y. because the change in the function can be replaced with the instantaneous rate times the change in the input, right? This can be rearranged. F prime of c is equal to f of x minus f of x y over x minus y. Okay, so this is the mean value theorem. And they're here where c is an element of x to y, okay? Fine. Then if I look at the absolute value of this thing, right? See what I have? I've got absolute value of 1 minus f prime of c over big M, right? Times x minus y. But notice the condition that was made on the derivative. What does that mean? Well, my f prime of c, it's somewhere in there, right? So how can I replace this with a constant, which is
that number is positive.
less than or equal to what? 1 minus what?
1 minus.
I want to make this
That's less than
as
1.
big as possible. I subtract the smallest thing possible, so I replace this not with f prime of c. What's the smallest f prime of c can be? It's actually smaller than f prime. And see the strict inequality here? So I just replace that with an m, little m. Does that make sense logically?
Yeah.
Okay. And there you have it. This is your k less than 1. Therefore, this is a contraction map. Which then we use the contraction mapping theorem, and I think that pretty much does it for us, right? Because the contraction mapping theorem says that xn minus x star is what? It is less than or equal to k to the power n over 1 minus k times the difference of x0 minus, x1, which here, that being my choice of k, I've got just some algebra to do here, right? So I've got like 1 over 1 minus m over m times, 1 minus m over m to the power n times xn minus x0, excuse me, that's supposed to be x1. I mean, it doesn't matter, it's absolute value, right? But x1 minus x naught. Okay, so how do you get from this to that? Well, what is x1?
x0.
It's f1 is x0 minus f of x0 over m, right? So you see this right here. This is literally f of x0 over m, right? Well, there's a minus, fine. So that's that. And then all that remains is just to do the algebra on this, which is, interesting. Well, I don't see right offhand why that I can replace this with just m. Maybe I've lost track of maybe that. Oh, hold on a second. All right, well, I'm not quite sure what happened there, but you can almost see it. I mean, I've got a big M here too, and if I copy this down right, it's a little m there. Of course, if I've got division by a larger number, I can make it smaller than the division by If I replace that with that's smaller than big M, that makes the fraction larger. Okay, that's not a problem. I just don't know why you'd do that. I'm a little bit perplexed why the estimate is written as it is. Maybe I'm just making a stupid a stupid error here. He says K is equal to 1 minus M over M. Yeah, that's what I said. All right. Oh, I can't do math. I'm a dummy. Look, it's just stupid. 1 minus K, right? What do I have here? Just K. I'm a dummy. So I'm supposed to do this, 1 minus that, right? The 1's cancel, and you've got M over big M, and then that M cancels with this M and leaves you little m. It's just literally algebra. All right. Last thing. Does this actually, you see, I claimed that it converges to that the fixed point of the fixed point of the iterate is the root. Is that clear? Like what happens when you have, see what happens here? When we have phi of x star equals to x star, right? Which is equal to x star minus f of x star over m. What does that tell you? That tells you f of x star must be equal to 0. So the start of every contraction mapping like argument is to look at what you're trying to find and try to like rewrite it as something you can iterate. So here, I mean, but you see, like you start here. It's not entirely obvious that you should go here, right? I mean, honestly, like this it's not that this leads to that by some sort of like obvious insight. The insight is Newton's method, and this is a twist on Newton's method. That's where, you know. All right, so there's that. Now, so the next part of this discussion requires some new ideas. And so here, let me show you how Edwards deals with the norm of a linear transformation. So we have dealt with the norm of a linear transformation by maybe insisting on bases which were nice. Edwards' analysis is all in Rn. So he's not going to mess with the basis. He just has to kind of mess with the norm, because he's not going to mess with Rn itself, right? So his way of making things nice is to just introduce the appropriate concept of norm. So here what I'm about to tell you is about the multivariable mean value theorem. So the first thing to know about this is it's not true in the naive sense. In other words, if you have f as a mapping, let's say from U, which is a subset of Rn, all right, to R, okay, that kind of function, a real valued function of a perhaps open subset of Rn, and you know, suppose that L as a line segment, all right, line segment, and then the natural mean value theorem to try to find would be this: f of b minus f of a, well, by golly, it ought to be equal to the gradient of f at some point c, right, dotted with b minus a. And here I'm using that L is the line segment from A to B. Okay, that notation. Let me be clear here. This is, A plus T times B minus A, such that 0 less than or equal to T less than the line segment, okay? Now, oh, this is actually true. My bad. This is actually true. What is not true? This is true. You can prove this. However, if we have like f as a, this, say n, it fails here. Let me use a g here just to give a different letter. So like g, if you have g of b minus g of a, it may not there, it may not be possible to find. It may not be possible to find. I guess I should just let it be. No, I can't do that. Son of a gun. I'm sorry. I want to look at a mapping from Rn to Rm. From Rn to Rm. Put an M here. All right, so I guess what I should probably put, I'm not sure what he has, but you can't say that this is equal to like the Jacobian of G, at some point C on the line segment times B minus A, all right? Or if you like, this would be dg, the differential at the point C of G acting on B minus A, all right? There does not exist C in the line segment, okay? Such that this happens. Now, that's, you probably should require me to give you an example. Like I owe you an example of why this fails, right? Right? All right, so it's probably easiest, I think the easiest thing to do, hopefully this will work. I'm a little worried. How about this? Like R of T equal to, I don't know. Cos T, sine T, T, all right? And we can look at like R of pi over 2 minus R of 0, right? That would be what? 1. All right, so that's negative 1, 1, pi over 2, right? So my claim is that there does not exist, some t in 0 to pi over 2, right? Such that dr dt times t, let me call it t star, no relation to the such that this dot what? This dot, this times pi over 2 watch me be unlucky here. All right, so what is dr dt here? It's like, yeah, you'd have sine of t star, well, minus sine of t star, right? Cosine t star 1 times pi over 2, right? Am I being fair? Would that be, the Jacobian matrix is just the, it's just the velocity vector in this context. All right, that is the Jacobian matrix. It's the velocity vector here. And I just multiply by the change in t as appropriate, which in our context would be pi over 2. So the question is, can you make, can you get this is equal to that? Well, I guess the pi over 2 worked out okay. I was expecting that to be the problem. But it looks like we need sine of t star, right? Equals to 1. And we also need cosine of t star equals to 1. There's just one problem. That's impossible. Yeah. So therefore, there does not exist. So I mean, basically, and I've done this before in such a way that I had like, well, anyway, I get this is fine. This is a good counterexample. But anyway, so this is the naive. This would be the naive multivariate multivariate mapping theorem, right? Which fails. However, what Edwards proves in about the next, I guess, 4 or 5 pages is that there is, in fact, a multivariate mean value theorem, and its statement is, I flipped past it. All right, come on, show yourself. Multivariate mean value theorem. I suppose it's this. Let f from U, a subset of Rn to Rm, be a mapping, be C1 map, which that means it has a derivative which exists and continuously so. So it's a continuously differentiable map, right? And U is open set containing the AB, all right? In other words, in his language, U is a neighborhood of the line segment, all right? Then, check this out. F of B minus F of A sub 0 is less than or equal to B minus A sub 0 max X an element of L of the norm of F prime of X.
And here this interval is a line in Rn.
A line, yeah, line segment in Rn with endpoints A and B. So the same thing I have up there. All right, so I mean, there's lots of notation here. I mean, there all kinds of questions that you got to answer. I mean, I have skipped past 3 pages of development here, right?